Diagonalization of matrix by N. Kaushik Reddy. What is meant by diagonalization of matrix? Matrix diagonalization is a process of taking a square matrix and converting into a special type of matrix, and so called the diagonal matrix, and that shares the same fundamental properties for the of the underlying matrix. And how do you determine the matrix is diagonalizable? So when we will call this matrix as diagonalizable or not? Whenever a matrix is diagonalizable, if and only for each eigenvalue the dimension of eigenspace is equal to multiplicity of eigenvalue. So whenever the each eigenvalue, the dimension of each eigenspace is equal to the multiplicity of eigenvalue. Meaning, if you find matrices with distinct eigenvalues, multiplicity is equal to 1. So if we have different matrix, then the multiplicity will be 1. You should quickly identify those as diagonalization. So we here see the diagonalization of square matrix. What is square matrix? Which consists of same number of rows and columns. Here is the formula of diagonal matrix, which represent the diagonalization is P D P inverse, where P is a model matrix and D is a diagonalizable matrix and A is the original matrix of the which is given in question. Remember that two square matrix A and B are said to be similar if there exists an invertible K into K matrix P such that B is equal to P inverse. And if two matrices are similar, then they have the same rank, trace, determinant and eigenvalues. So whenever we find some two matrices are similar, then the determinant of the matrices and trace and same rank and eigenvalues are same. Not only two similar matrices have the same eigenvalues, but their eigenvalues have the same algebraic and geometric multiplicities. And relation to eigenvalues and eigenvectors. So what is the relation between these eigenvalues and eigenvectors? We can write the diagonalization P inverse as AP is equal to PD. So when we take a straight line, AP is equal to PD. The kth column of AP is equal to AP dot K, where the AP dot K is the kth column of P. If you are puzzled, revise the lecture on something website, and the kth column of PD is equal to PD dot K, where D dot K is the kth column of D. The matrix used in the diagonalization must be invertible. So what is invertible matrix? Invertible matrix is A inverse equal to A into A inverse is equal to I, A inverse into A is equal to I. So the matrix used in diagonalization must be invertible. So whenever it performs the diagonalization, the matrix should be an invertible matrix. Therefore, its column should be linearly independent. And stated differently, there must be linearly independent eigenvectors of K. In the lectures of the linear independence of eigenvectors, we have discussed the fact that for some matrices called defective matrices, it is not possible to find linearly independent eigenvectors. So some defective matrices are there which is not possible to find linear independent vectors. So the eigenvectors are not linearly independent, they are linearly dependent. A matrix is effective when it has at least one repeated eigenvalue whose geometric multiplicity is strictly less than its algebraic multiplicity. It's also called as defective eigenvalue. So we see how to diagonalize a matrix. Suppose we are given a matrix A and we are told to diagonalize it. How do we do it? The answer has already been given in the previous proof, but it's worth repeating. We provide the answer as per the diagonal. Compute the eigenvalues of A. First, we have to compute the eigenvalues. Eigenvalues are eigenvalues are mm, eigenvalues are evolved from the formulas we read in before second linear transformations, and the check that no eigenvalue is defective. So no eigenvalue should be defective. If any eigenvalue is defective, then the matrix cannot be diagonalized. You can go to the next step. Otherwise, you can go to the next step. For each eigenvalue, find as many as linearly independent eigenvectors as geometric multiplicity of the eigenvalue. The number is equal to geometric multiplicity of the eigenvalue, and we should adjoin all the eigenvectors so as to form a null full rank matrix. So it should have full rank matrix R. Suppose we take R, and we should build a diagonalized matrix D whose diagonal elements are eigenvalues of A. So from the eigenvalues of A, we will build a diagonal matrix D, which is of same rank and which is of same order. Then the diagonalization is done where D is equal to P inverse A P. First important is we need to follow the same order when we build P and D. If a certain eigenvalue has been put at intersection of the kth column and the kth row of D, then its corresponding eigenvector must be placed in kth column. The important application here is the most important application of diagonal matrix is computation of matrix powers. So we should be conscious when we do the computation of matrix powers. Here we take, let D be a diagonal matrix and D equal to some diagonal matrix which has only diagonal elements and other elements are 0. Then its nth power can be easily computed by raising its diagonal elements to nth power. So d power n is equal to d power n 1 1, like that the matrix followed. If a matrix A is diagonalizable, then A is equal to PD P inverse, and what An will become is Pn PD P inverse into PD P inverse into, like that, up to n times it will multiply by n times, and the value will get is P d power n P power minus 1 P inverse is also called. Thus we all have to do to raise A to the nth power is to diagonalize. First we have to diagonalize A. If possible, to raise the diagonal matrix D to nth power, which is very easy to do, or we should pre-multiply the matrix D thus obtained by P and post multiply the P inverse. And here algebraic and geometric multiplicity. In this subsection, we give a variant of diagonalization theorem that provides another criterion for diagonalizability. It is stated in the language of multiplicities of eigenvalues. In algebra, we define the multiplicity of root lambda of polynomial f lambda to be the number of factors of lambda minus lambda norm that divides f of lambda. In the polynomial, let's take a polynomial lambda cube plus 4 lambda square minus 5 lambda plus 2, and the roots of this are lambda minus 1 and lambda minus 2. The root here lambda not is equal to 2 as multiplicity 1, and the root lambda 0 is 1 as multiplicity is 2. So different has different multiplicities. So what is this definition? Let A be n into n matrix and lambda be an eigenvalue of A. Then the algebraic multiplicity of lambda is its multiplicity as root of characteristic polynomial of A. The geometric multiplicity of lambda is the dimension of lambda eigenspace. Since the lambda eigenspace of A is null of A minus lambda log n, is its dimension is the number of line variables in the system of equations A minus lambda into n x is equal to 0. The number of columns without pivots if the matrix A minus lambda in. Diagonalization theorem variant. So what is the other variant of this diagonalization theorem? Let A be n into n matrix and the following should be equivalent. A is diagonalizable and the sum of geometric multiplicities of the eigenvalues A is equal to n, and the sum of algebraic multiplicities of the eigenvalues of A equal to n. For each eigenvalue, the geometric multiplicity is equals to the algebraic multiplicity. Geometric multiplicity is always equal to the algebraic multiplicity. Diagonalizable matrices are similar if and only they have same characteristic polynomial or equivalently the same eigenvalues with the same algebraic multiplicities. So when the diagonalizable matrices are similar, they have same characteristic polynomials and equivalently same eigenvalues and same algebraic multiplicities. For example, diagonalizable matrices with same entries are similar. So same entries means same elements in different ways. Any two diagonal matrices with the same diagonal entries, possibly in a different same order, are only similar to each other. Indeed, such matrices have the same characteristic polynomial. So this is the topic which is involved in this diagonalization of matrix. The main aim is we should do the model matrix P and one diagonal matrix, and the diagonalization is equal to D equal to P into A P inverse. This is a formula which we have to remember for last. So thank you for giving this opportunity.